Hello everybody, I'd like to talk about a new subject in statistics. It is regarding the linear regression using the least squares. In a previous presentation, I have talked about the way of predicting the equation for the linear regression straight line. Now we talk about the linear regression line, but with the relation with the least squares. First of all, what we have here, we have a set of data. We have 5 observations, and we compute all the computation in order to get for the slope of the linear regression line and regarding the y-intercept. So we draw here the linear regression line. As we see here, for each value of x, we have 2 values of y. For example, for x equal to, we have 2 values for y. The first one is the actual value, which is simply y, and we have another value, which is the predicted value, which lies on the regression line. So here we have what's called y, and here we have what's called the y hat, because it is the predicted on the regression line. So we have here an error, which is simply the difference between the actual value and the predicted one. So this is called E2. Same for x equal 3. We have 2 values for y. We have this value here, which is the actual value of y, which is simply 1, and the other value is the predicted one on the regression line, and the difference between these 2 points represent the value of the error. So as you see here, sometimes the actual value comes to the top of the linear regression line, sometimes it becomes below it. So we have some values for the error to be positive, sometimes it is negative. So in order to ignore this conflict, we simply square all of these values of error and sum up all of them. So we have the total of the square of the values of the error. So if you try to compute the total or the sum of the squared of the errors, in this case you will find the least squares by using the regression line. If you try to change the formula of the regression line, means you change the slope and the intercept and compute the squares of the squared of the errors, you will compute the value to be greater. So the regression line should have the lowest possible value of the sum of square. And the sum of the squares for the error is simply the sum of E1 squared plus E2 squared plus E3 squared plus E4 squared plus E5 squared. And this sum should be as minimum as possible. So this is the formula to compute the sum of squares for the error. For example, for the first observation, for x equal to 1, we have two values for y. The first one is the predicted one, and it is calculated by using the regression line formula. And the second value is the actual one. So the value of E1, which is the error 4.1, is simply the predicted value minus the actual value, which is y1 hat minus y1. So in order to ignore the conflict of the sign of the error, we take the square for E1. So E1 squared is equal to y1 hat minus y1 all squared. Let's understand all of these concepts by solving these questions together. We have here a data and 5 observations for both x and y. The first part of the question is to display the scatter plot. The second is to compute the Pearson's correlation coefficient. Actually, we talked about the way to compute for the Pearson's correlation coefficient, but I will go quick. The third part is to find the equation of the regression line. The fourth part is to draw the regression line. Number 5 is to predict the value of y, which is y hat, for x equal to 7. Then he asked to compute the error of prediction for x equal to. Then he asked to compute the least squares of the errors, of course, by using the regression line. And finally, we need to compute the squares or the squares for the following equations, and these equations are not the same as the regression line. So we need to conclude what happened to the squares of the error in case of changing the formula of the line. This is the first part. This is the display of the scatter plot. As we see here, we can conclude simply that there is a positive relationship between the two variables, x and y. So we have a positive correlation. Now we can simply compute for the Pearson's correlation coefficient. We should make the square for both x and y and multiply x times y and take the sum of all the observations. This is the formula we have used in order to compute for the Pearson's correlation coefficient. Now we can simply substitute all of these values. We have here 5 observations, so n equal to 5. This is sum of xy, 58, minus sum of x, which is 16, times sum of y, which is 15. All of these are divided by the root square of, this is n, this is the sum of x squared, this is the sum of x all squared, multiplied by n, sum of y squared minus sum of y all squared. If you proceed, you will get the value of the correlation coefficient to be about 0.70. So in order to understand this value of correlation, simply we say that we have a positive correlation, which means that as the value of the variable x increases, so does the value for y. And regarding the strength of the correlation, 0.70 is about to be a moderate correlation. So the interpretation for this value of correlation, it is simply moderate and positive correlation. The third part is asking for the equation of the regression line. So this is the general formula for any straight line. And of course, the regression line we have is also straight. So we need to know the value of the two constants, which is the value of m, which represents the slope of the regression line, and small b, which represents the y-intercept. This is the formula in order to compute for the slope of the regression line. We can simply substitute. This is n. We have 5 observations. This is the sum of x times y, 58, minus sum x times sum of y, all divided by n, multiplied by sum of x squared minus sum of x all squared. So if you proceed, this is the value of m, which is the slope of the regression line. Now we can simply compute for the value of b, because computing the value b depends on knowing the value of m. So now we need to determine the value of b. This is the formula to compute for the value of b, which is the y-intercept, sum of y minus m, sum of x, all divided by n. This is the sum of y, it's 15. This is the calculated m, it's 0.68, and this is the sum of x, and we have n 5. So the value of b is equal to 0.82. So now we know both m and b, so we can simply know the formula for the regression line. It's y hat equal to the 0.68 multiplied by x plus 0.82. So this is the way how to find the equation for the straight regression line. Here the regression line, it is drawn. So as you see here, this is the value of the slope for the regression line. It is 0.68, and this is the y-intercept. The y-intercept is simply 0.82. Regarding the slope, which is 0.68, simply you can compute if you know 2 points on the regression line. For example, this point number 1 and this point number 2. If you know the value of the variation of y, this value, it's called delta y, and you know the value of the variation in the values of x. This is delta x. So if you divide delta y by delta x, you will get the value of the slope. It is simply 0.68. As I have said, if you try to compute for the squares of the errors for the 5 observations, you will find the least value. The fifth part of the question asks to predict the value of y hat for x equal to 7. Notice that x equals 7 is not belonging to the defined set of x values, and it is outside the range of the defined values of x. So we are saying that we are making an extrapolation. So for the value of x equal to 7, we need to know the value of y hat. We only have one value of y, which is the predicted one on the regression line. So our process is called an extrapolation. In order to determine the value of the predicted y, simply we substitute in the regression line formula and substitute for x equal to 7. So the value of the predicted y is equal to 5.58, which means that if you try to determine the intersection between the value of x equals 7 and the regression line and draw a horizontal line, you will get the value of the y hat. It is simply 5.58. Now we ask to compute the value of the error of prediction for x equal to 2. As I have talked, for x equal to, we have two values of y. The first one is the actual one, which is y equal 4, and the second one is the value of the predicted y on the regression line. So point number 1, the height of point number 1 is known, it is 4. So we need to determine the value of y, the predicted y for x equal to. So we can simply use the regression line formula and substitute for x equal to 2. So the value of the predicted y is simply 2.18. This means that if you draw a horizontal line from the intersection, you will get the predicted value, which is 2.18. So this point is 2.18, and this value is simply 4. So the value of the error is simply the difference between these two values. So we know the actual value to be 4. So the error of prediction, which is capital E, is equal to the actual value minus the predicted value. This is the actual value, it's 4. And this is the predicted value, it is 2.18. So the value of the error is simply 1.82. if he asks you to square this value of error, simply we can square it in order to compute for the squares of the error. Now he asks to compute for the least squares of the errors. Here we have 5 values of errors. For point 1 we have E1, for point 2 we have E2, for point 3 we have E3, for point 4 we have E4, and for the last point we have E5. So for each of these values of e's, we need to determine these value and square them. For example, for x equal 1, and in the table above, here we have x equal 1 and y equal 1. Here y represent the actual value, so we need to determine the predicted 1, so we compute by using the regression line formula, which is 0.68 times x plus 0.82. So we put instead of x1, and finally we can get the predicted value of y hat. So the value of E1 now is simply the difference between these two values. Then we square this value. So regarding the first observation, for x equal to 1, this is the predicted value, it's 1.50. So this point here is 1.50. And the value of y is simply 1. So the value of the error represent the actual value, which is 1, minus the predicted 1, which is 1.5. So the value of the error is minus 0.50. See that we have some errors are negative and some are positive. It doesn't matter because we need to take the square of these values. So if you square this value of E, which is E1 squared, it is 0.25. So 0.25 represent the value of E1 squared. For the second value here, this is simply the value of E2 squared, and so on. If you try to sum up all of these squared values of E, you will get this value, which is 7.24. So 7.24 represent the total sum of the squares of the errors. And this value is the least one. This is why the title of the least square, which means that if you try to change the regression line, which means you use another line with different values of m and b and try to do the same procedure here, you will have a summation of the squares of the error to be more than 7.24. Let's understand this concept. Now we change or we use another straight line. This is simply new straight line with formula of y equals 0.56x plus 1.26. So this is the slope of the new straight line, and this is the y-intercept. And if you see here, this is the value of the y-intercept. And of course, we keep the observations same. So we need now to do the same procedure we have done before in order to compute for the values of the squares of the errors. So in this case, this is the value of E1. This is the actual value, 4.1. And this is the predicted one on the new straight line. So the value of E1 can simply be computed by knowing the y value for this point, of course by using the formula in the above, and subtract this value from the actual one. So this value represents E1. Of course, we are interested in the square of E1. So having the square of E1 is simply same like drawing a square with the side length of E1. So this is E1 and this is E1. So the area of the square here represent E1 squared. Same we do for the second point for x equal 2. This is the value of the error. This is E2. It is easily can be computed. We can compute the predicted value on the new straight line, but we are interested in the square of E2. So this is another value of E2. So we have now a square, and simply we can compute for the area of this squared, which is the representation of E2 squared. If you do the same steps for all the rest observations and sum up all of these squares, you will find that the sum of the squares is 7.45. See that this value of the sum of square is greater than this value, which is calculated but using the regression line. So if you try to change the formula of the line, you will have a sum of squares to be greater than the optimal one by using the regression line. Let's have another formula of straight line. We have this new straight line, y equal 0.29x plus 2.2. So the slope now becomes 0.29, and the y-intercept is 2.2 on the y-axis. So as you see here, the value of E1 has been changed in comparison with the previous steps. So this is the new value of E1. So a1 squared is simply the area of this square, and this is the value of the error for the second point. This is the value of the error for the third point, and this is the value of the error for the fourth point, and this is the value of the fifth error. And if you try to square all of these errors, so you will have 5 different areas of 5 squares. So if you sum up all of these areas, you will get the sum of squares, and now we have a new sum of squares. We have 9.53. So as you see here, the sum of the squares of the error becomes greater than the previous one, and the optimal value of the least square are the calculations, but with the using of the regression line. So this is the conclusion of our presentation. So the conclusion now, if you try to draw the regression line for some observations and try to compute the squares of the error, you will have the least value. If you try to use another straight line instead of the regression line and compute for the sum of the squares of the error, you will have more than the optimal one. That's all about the regression line with the least square. Thanks a lot for you. Thank you for watching. Goodbye.